Hello, welcome to the next lecture. So in this video, I'm going to cover the following topics: local search algorithm, variable neighborhood descent, and taboo search. So actually, variable neighborhood descent and taboo search is the part of your syllabus. Both these algorithms, both are search algorithms of course, and both these algorithms are nothing but local search algorithms. So initially we will be seeing what do you mean by local search algorithm. Okay, let us revise a bit about heuristic search or informed search. We remember heuristic search uses certain heuristics, right? So in this kind of search we have already studied, you must have seen the video of hill climbing algorithm. So hill climbing algorithm, taboo search, simulated annealing, these are all heuristic algorithms. Okay, hill climbing, taboo search is the part of your syllabus. Best first search algorithm we have already seen in one of the videos. Okay, so it uses heuristics. A star algorithm, this is also we have studied. So these all algorithms are based on heuristics. Further example is greedy search algorithm. So these are basically heuristic search algorithms. Among these, best first search, A star we have seen. Hill climbing, I've already posted videos. Okay, in this video also I'll give a brief description of hill climbing. Taboo search we are going to see here. Okay, simulated annealing and this we'll see later on. Find the solutions quickly. What is the importance of heuristic algorithm? That we can find solution quickly and often we get better solutions. So of course these algorithms are far more better as compared to uninformed search. So local search algorithm, as I said, taboo search, hill climbing, these are all local search algorithms. So we need to see first of all what do you mean by local search. In computer science, a local search is heuristic method for solving computationally hard optimization problems. Okay, so the problems which are computationally hard, okay, optimization type of problems, in order to solve these kind of problems we use local search. They start from a perspective solution. Okay, any one solution like this could be a solution. They started from there and then they move to the neighboring solution. Okay, for example, I start from here, then after that I'll go to the other part, like neighbor, in this particular neighborhood. Okay, if I start with this, I go here, next I go there, this solution is better, then I feel this is better, then I feel this is better, like I move from one place to the other. Okay, so initially you have to start with prospective solution and then you go to the neighboring solution. It keeps a current state, okay, and gradually always it tries to improve the current state. So it calls the current state as x. Okay, so later on it will find the another state x dash. Suppose this x dash is better than x, then x dash will become my new current state. Here we have objective function also. It tells us how good a given state is. Okay, its goal is to find the goal, we need to maximize or minimize this function. In order to reach our goal, we either increase this function or we decrease the function. Example, if you know what is hill climbing, if you have seen that video, okay, if I'm over here, my objective function is to maximize. So each time I'll go to the other state so that I get a better solution. So in this case I'm maximizing my objective function. Okay, keep smaller number of nodes in memory. Yeah, here we need to keep certain nodes in the memory and used when solution is goal state, not the path. Okay, so local search algorithms move from solution to solution in search space. You know, we have search space. Okay, so if you feel like this is a solution, next time you feel like this is a solution, next time you feel like this is a better solution, Okay, so it goes from one solution to the other by applying local changes. Okay, local changes means what? Changes applied nearby areas. Okay, until you have to do this until you get certain target solution or your time bound is elapsed. So till your time, you have time or you get solution, you have to repeatedly move from solution to solution. Okay, you remember TSP problem we had solved using nearest neighborhood algorithm. So what is nearest neighborhood algorithm? We tried to find locally. It's a local search. So for TSP, again you must have in second year you have studied about vertex cover problem. So vertex cover problem, TSP problem, we can solve using this strategy. Okay. So I can state that your local search algorithm starts with a candidate solution. Candidate means one example solution. Okay. It iteratively moves to the neighboring solution. Fine. Now, which solution to take among neighboring solution? For example, I have n, suppose this is my search space. This is my first solution which I feel like this could be a solution. So I'll call it as prospective solution. Okay. Now, which neighborhood to go? I can go to this, I can go to this, I can go to this. Like where to go? This is one question. So answer depends upon which strategy is being used to solve this local search. You can solve it using hill climbing, you can solve it using taboo search and so on. Okay, so it depends upon which algorithm exactly you have implemented under local search. So what do you mean by local searches? If I get a solution locally, I have to find for better solution. Okay, so if I feel like this solution is better according to my strategy of which algorithm is used. If I apply hill climbing, I'll go from here to here because I feel this solution is better than this solution. Okay, so locally I have to search for a better solution. That is nothing but local search algorithm. Fine. So if just examine, just imagine if you are getting no solution. Okay, if you have no solution, so you will be stuck at local optimal point. That is one problem with this local search. So its answer is either we should restart the local search or we can iterate the local search. Fine. So this local search, if I apply in increasing fashion, okay, so my local criteria is I want maximum criteria. Suppose I'm over here, I want more than that, I want more than that. Each time I'll select the solution which is more than my current state. So in this way I'll go to the top of the hill. Okay, so hill climbing is nothing but it's an iterative algorithm that starts with certain arbitrary solution. Okay, arbitrary means any random solution. I start from over here, for example, and it attempts to find a better solution by changing a single element of solution increment. Next time I feel this to be better, so this will become my current state. Each time I'll compare my new state with my current state. If the change produces a better solution, incremental change is taken in the new solution. So I go there. This process is repeated until there are no further improvements. It uses loop that continuously moves in the direction of increasing value. Means my loop is going to go in this direction and it will terminate when I reach to peak. So how will I understand that I have to stop over here? Because this is going to be my current state. Current state will be compared with the next state. So I'll find that next state's value is less as compared to current state, whereas my criteria is to maximize, and hence this is the peak. What I opt to reach, I have reached it. Okay. Now the problem with this is not complete or optimal. So I have prepared a separate video on hill climbing algorithm. You should refer that particular video to get insight of this. Okay, it is not complete, it is not optimal because it doesn't guarantee that each time I'll get the best solution or each time even I'll get solution. I'll just given one example over here for hill climbing search. This is my start node. Okay, I want to reach over here. So from over here I go here, here, here. So this is going to be my search path in this fashion. Fine. And and my length will be 1 plus 2 plus 3. In this fashion we will come down. Okay, so down is nothing but my top of the hill, because this was my goal and this was my start state. Fine. So you better refer a separate video for hill climbing. So next we have simple neighborhood descent. In this video, in this algorithm, simple neighborhood descent, here our goal is to maximize f of x. F of x is certain function. My goal is to minimize it. I want its minimum value. So what will I do? I will go to my neighbor points in the neighbor. Okay, that will improve my current objective function. What is my objective function? That I want to minimize this f of x. So I'll go to the neighbor where I feel like f of x is less than current f of x. Okay, and it will end when no improving solutions can be found. The final x obtained by this method is called as local optimum. Just check here, this is my value of x. I'll go from this value to this value because here f of x is less as compared to this f of x. Okay, but this doesn't guarantee that I'll get a good solution. Okay, local optimum is a problem. Like if I find कि within this neighborhood this is the least, but what about the rest part of my search space? I have searched only one neighborhood. Okay, so the solution what I get is nothing but local optimum. Okay, locally it has given me minimize one. Fine. So for whole search space this algorithm will not work. So I need to go to variable neighborhood descent. Okay, now this is meta heuristic approach. A meta heuristic, okay, it is in trends nowadays in artificial intelligence. It is high level problem independent algorithm framework, or in short I can call it as framework for building heuristics. Okay, that means it provides us guidelines in order to develop heuristic optimization algorithms. You don't have to know this in, okay, develop means using this heuristics, meta heuristics, we can develop heuristic optimization algorithms. So let us consider a combinatorial problem. Here I am trying to explain you mathematically about what is that optimization problem and all. So what is my aim? I want to find minimum of f of x such that this x belongs to, here this is belongs to capital X, where f of x is the objective function that I want to minimize, and capital X set of the feasible solutions in my search space. So this is one solution, x star. Okay, it belongs to x is optimal if, means this is my solution if for all the values of small x belonging to capital X, means for every value of small x belonging to capital X, I want that f of x star should be less than equal to f of x. Okay, so I'd like to repeat what it is. I want to find minimum value of f of x. X is nothing but my point in search space. Okay, for every point in my search space, I want that f of x star should be less than equal to f of x. So this f of x, if this condition is true for each and every value of x in my search space, then I say that x star is my optimal solution where I wanted to minimize the value of f of x. We'll continue in next video. Thank you.